hope it is visible to all of you.
Yes, sir.
Yes, sir, visible.
Why I can see records? What happened? So last class it was the same problem.
Sir, we can also record by pressing Windows Alt and R button.
Windows?
Windows Alt and R.
No, I am using Ubuntu. So will it work?
Sorry, sir, I don't know.
Because whatever you are saying, it is valid for MS or Microsoft or Windows operating system, but it's Linux operating system. Normally it appears here, this panel.
Sir, in the other classes, we click the join button to join, but here we are joining by the link. It may be because of that.
No, because if you look, even if this problem happened since last lecture, if you remember, right? So
Yes, sir.
I have to figure it out. Because normally these three dot buttons, this is microphone, this is okay. Probably I should ask our system, administrator, because he might have said something. But we are using our institute, email address. Activity. So here, why the red is coming here? Okay, anyway, so let's continue today's lecture. Maybe once the lecture is over, and probably in the evening I'll try to fix it. Why to? What is it? This is nothing. So the lecture slide is visible, right? Is it visible?
Yes, sir, visible.
Yes, sir.
Yes, sir.
Okay, just a brief the summary. Whatever we did discuss on double refracting crystal. So it produces a couple of plane polarized light in the process of transmission, or you can say the process of refraction. And these are some important properties for any arbitrary angle of incidence, right? And then we said there must be an optic axis along which there will be no concept of double refraction, as we proved by this using this relation. So the velocity will remain same. And so if somebody will ask question, what will happen for normal incidence, right? And then normal incidence, any arbitrary angle to optic axis, normal incidence along the optic axis. So these are, you can say, the two special cases. What will happen, these two plane polarized light. Am I audible?
Yes, sir,
Yes,
audible.
sir.
Okay. So now you can look at these couple of diagrams. what you can see that this you can see the angle between the incident beam and the optic axis is theta. So this, right? So theta is an arbitrary, and since it is a normal incidence, so the ordinary ray will travel without deviation, but the extraordinary ray, so it will deviate, right? As shown this blue color lines, and these red dots represent the electric field oscillation direction associated with O ray is perpendicular to this plane of paper. Okay, and here the E ray oscillation direction lies on this plane of paper, or you can say the laptop or this presentation slide. Okay, and as I said, for simplicity, let's optic axis lies on the plane of paper, and therefore, and K, this profile also remains on the plane of paper. And since you know it is not along optic axis, although it is normal incidence, so therefore they will travel unequal velocity v not equal to v1. Okay, so now and if somebody will ask question, if we rotate the crystal or the double refracting, so whenever I'll say crystal, you'll understand it is, you know, a double refracting crystal. If you rotate this double refracting crystal around its axis, what we'll see that the extraordinary ray will rotate around this as shown here. Okay, so the extraordinary ray will rotate around the ordinary ray beam. Okay, because the optic axis will rotate and therefore the extraordinary will also rotate. So rotation of double refracting crystal about the incident beam or along the axis rotates the E ray around O ray and therefore produces a surface of cone. So the extraordinary ray will produce a surface of a cone, a conical shape. Okay, whereas the ordinary ray will still travel without any deviation as per, you know, the law of the laws of transmission or refraction. Okay, so now let's see that we have normal incidence along the optic axis and the perpendicular to the optic axis. Okay, so when we have along the optic axis, so there will be no concept of double refraction. The velocity v will remain vo. Okay, so the velocity of ordinary ray will remain velocity of extraordinary ray because there will be no concept of double refraction. And you can see, you can think about non-polarized light will have been a mixture of ordinary and extraordinary ray. Okay, and what will happen if, you know, it's a normal incidence and perpendicular to the optic axis? And if you know, remember or use this couple of relations, right, this couple of relations, so what you'll conclude by putting theta equal to pi by 2, the cos pi by 2 will be 0, so this will be that, and hence the E, right, the refractive index will have mu E, which is a constant, and the velocity, if you put, it will satisfy this relation. So what does it mean? So let's say here, so it means that mu O ordinary ray will remain mu O, whereas mu E will satisfy this relation, and if you put the theta angle, then it will be mu, because cos pi by 2 will be 0. Still the mu is mu E square, so but mu not equal to mu E, so therefore what will happen, the velocity will unequal. So what does it mean? Although both rays travel without any deviation, what will happen that they will not leave the surface of double refracting crystal simultaneously. One of the ray will come out initially compared than other. So which ray will come out initially? That depends on the type of double refracting crystal. If you have a quartz, which is a positive, then ore will come out first. If you have a calcite, which is a negative double refracting crystal, ire will come out first. But the message is, if if we have normal incidence perpendicular to the optic axis, both ray will come out without any deviation with unequal velocity. But if along optic axis, both ray will come out with simultaneous because they travel with equal velocity or speed. Okay, so whatever I said, it I have written down them. So both rays travel in same direction without deviation and with the same velocity. So this case, both rays travel in same direction without deviation and with different velocity. Since the velocity of extraordinary ray is equal to ordinary ray, they travel same optical path inside a double refracting crystals. Whereas since the unequal velocity, they see different optical paths inside double refracting crystal. That means the phase difference can be created if we have a normal incidence perpendicular to optic axis, because they travel different velocity. So therefore, both rays emerge simultaneously from the surface of double refracting crystal or normal incidence perpendicular, along the optic axis, whereas perpendicular in the case of perpendicular to optic axis, they will emerge, both rays do not emerge simultaneously from the surface double refracting crystal. How do you explain? And the E-ray electric field oscillation direction and the optic axis remain in the same plane as per the definition, and electric field direction is perpendicular to the optic axis. Okay. O-ray electric field oscillation direction is always perpendicular to the E-ray, and therefore it will remain the oscillation direction perpendicular, it also perpendicular to the optic axis. If you look here, right, the both cases, the oscillation direction is perpendicular to the optic axis. One will remain the plane of incidence and another will be perpendicular to the plane of incidence, but both oscillation direction is perpendicular to the optic axis because the the incident is along optic axis. For this case, what we'll have, that E-ray will oscillate along the direction of the optic axis, whereas O-ray will oscillate perpendicular to the optic axis. And the short message here is, one can see that a path difference between E and O-ray can be created by normal incident, by incident normal unpolarized light perpendicular to the optic axis. If you have a normal incidence perpendicular to the optic axis, one can create the phase difference between, or sorry, path difference, and therefore phase difference between E-ray and O-ray, which are basically two different type of plane polarized light. Is this clear so far? Am I audible?
Yes, sir. Yes, sir.
Yes, sir.
So then the next question is, what will happen if we incident a plane polarized light on a double refracting crystal? Whatever we have explained or discussed, for that is true for unpolarized light. And what will happen? You have plane polarized light. So, whatever we discuss on polarized light, this will also be applicable to plane polarized light. Okay, that means if you have a normal incidence perpendicular to optic axis, then one can also generate two components of it as a plane polarized light, two plane polarized light. So let's discuss in great detail these particular special cases, namely normal incidence perpendicular to the optic axis, because this way one can create a path difference between O-ray and E-ray. Okay, so first we have to look this diagram. So what does it indicate? So it says that the the plane polarized light, which is incident on the perpendicular, as it says the normal incidence, perpendicular incidence, and again perpendicular to the optic axis. So this cyan color represents the optic axis direction, and the Z represents, it's a three-dimensional, right? So Z represents the propagation direction of the incident beam, which is plane polarized, right? And we have y-axis and x-axis. Okay, so here the y-axis is coming out from this plane of paper. So therefore, we have given the direction. Okay, so here, so this diagram. So y-axis coming out from the plane of paper. X-axis, from left to right. Z-axis from top to bottom. The direction of propagation of the plane wave. Okay, so now, since it is a plane polarized light, first of all, we would like to know what is the electric field oscillation direction. So let's assume the electric field oscillation direction is along x-axis. You can see, right? I have these symbols. And the second case, along y-axis, as the y-axis coming out of this plane of paper. So you can see the this dot. And then the third case is any arbitrary angle theta. So this is along x-axis, this is along y-axis, and here the plane polarized light oscillation direction makes an angle theta with respect to what? This we can say x-axis or y-axis, or x-axis here, theta angle. So this three schematic diagram is clear to everybody? Yes or no?
Yes,
Yes,
sir.
sir.
Here again I am repeating, the oscillation direction of this incident plane polarized light is along x-axis, here along y-axis, and any arbitrary angle theta, right? The oscillation direction electric field with respect to x-axis. Okay, so look at this. And since it is along x-axis, so therefore, and here the optic axis is also along x-axis. So when it will emerge out, then this beam will emerge out. Which beam? Which ray? So it will emerge out as a E ray, because the E ray oscillation direction is along optic axis. If you look this case, so the E ray right here, the E ray is along the optic axis. Okay, normal incidence perpendicular to optic axis. So it means that if if a X polarized light is incident on a double refracting crystal, normal incident of course, and perpendicular to the optic axis, where optic axis also directed along x-axis. So this case, the plane polarized light will emerge out as E ray. Okay, so this X polarized light will travel inside double refracting crystal as if E ray, and this Y polarized light will emerge out as O ray inside double refracting crystals. So what we learn, if we have a X polarized light, then when it travels inside double refracting crystal, even if after leaving the surface of double refracting crystals, so it will emerge out as E ray, whereas for Y polarized light, O ray. Is this clear to everybody? Yes or no?
Yes, sir.
Everybody understood this concept?
Yes, sir.
So now, if somebody will ask you question, any arbitrary angle of incidence. So it will have two components. Okay, so here, theta. Okay, so now it will have two components along, because we can, make it two components along x-axis and along y-axis. Yes or no? So if this the electric field is E, then we have E cos theta, and this one will be E sin theta. So any arbitrary angle that makes with respect to optic axis, that it will travel, right? This plane polarized light will travel as if it has two components X and Y, and inside double refractive crystals, these X and Y components associated with the plane polarized light will behave as E ray and O ray. Okay, so the component which is along optic axis, for this case X axis, we have E ray, and the component which is perpendicular to the optic axis, in this case the Y axis, we have O ray. So what we understood that if we incident a plane polarized light with any arbitrary angle with respect to optic axis, of course we have normal incidence perpendicular to the optic axis. So this case, what we'll have, then the plane polarized light will travel as E ray and O ray inside double refracting crystals. Okay, and of course when they will leave the surface of the double refracting crystal, and since they travel on equal speed, so automatically the phase difference, phase difference is created between the E ray and O ray. So now when they'll emerge out, we'll have X component or Y component, and then the phase difference between them. And we can use the concept of the phase difference between two component wave. If you remember the mathematical analysis of the different kind of polarized light, and if the phase difference is pi by 2 with Ex component equal to Y component, then we can say circular polarized light, otherwise we have elliptical polarized light. So now the concept here is one can produce either circularly, elliptically, even if you plane polarized light by using a double refracting crystals. So whatever I have said, we'll explain in great detail now. Okay, so I have already explained, right? So how come they will be E and O ray when they travel inside double refracting crystals, and when they will leave the surface of double refracting crystals, E ray will behave as your x-axis if the optic axis is along x-axis, and O ray will behave as y-axis. Sorry, y component of the incident plane polarized light. Okay, let me read it out. So when a plane polarized light is incident normally and perpendicular to the optic axis, by the way, am I audible?
Yes, sir. Yes, sir.
Yes, sir, audible.
So listen very carefully. So when a plane polarized light is incident normally and perpendicular to the optic axis, that means alpha is 90 degree, it will split into two plane polarized light inside double refracting crystals. One is E ray, electric field direction along optic axis, another is O ray, electric field oscillation direction perpendicular to the optic axis. But they travel same direction without deviation and with different velocity. Okay, and that has been represented through this schematic diagram. Okay, so you imagine the light is traveling from bottom to top, right? And we have plane polarized light. Okay, here the electric field oscillation direction makes an angle theta, which is fixed with respect to x-axis, and optic axis along x-axis. So now the O ray oscillation direction will be along y-axis, and the E ray oscillation direction will be along x-axis. Now the E ray will be called as Ex component, whereas O ray will be called as Ey component. So that has been written down here. The E, initially we have two components, and inside double refracting crystal E ray and O ray. So now so this is the three-dimensional representation. Okay, so this this color, right? So that which makes a theta with respect to optic axis, and this thick line, right? If there will be no double refracting crystals, and since you have double refracting crystal, you have two component, E ray and O ray, and you can see, so the phase difference are already created when they travel inside the double refracting crystal of path difference. And this concept, as I said, used to produce different kind of polarized light. Okay, and this principle, is used, right? If we cut or prepare a double refracting crystals in this way, and then that will be called as your wave plate. So it means wave plate is nothing but a double refracting crystal where the surface or the face of the double refracting crystal is, what will be the face of the double refracting crystal, or you can say the optic axis, is along the face of the double refracting crystals. Got it? Yes or no?
Sir, can you repeat once again that wave plate part?
So now, if you look here, so the optic axis is perpendicular to the incident beam, plane polarized light, or in general unpolarized light, and it is a normal incidence. What is the meaning of normal incident? When we incident a beam of light perpendicular to the surface or perpendicular to the interface of two media. So here we have air and then we have double refracting crystals. So it means the incident beam propagation direction is perpendicular to the surface or the face of the double refracting crystals and perpendicular to the optic axis. What does it mean? It means the double refracting crystal optic axis is along the or you can say so it is parallel to the plane or the face of the double refracting crystals. So here is the face and optic axis. Here this could be along x axis. So now it does not make any angle with respect to the face. And if we construct such type of double refracting crystals, if we cut or if you make the face in a such way that it aligns with optic axis or vice versa, you prepare a double refracting crystal where the optic axis will align to the surface, then it is called wave plate. Because when you incident normal incident, then this this phenomenon can occur. That means it will split into two components as E and O ray. Got it?
Yes, sir.
So here you can see the surface here. Okay, so here the surface, and the surface is along the optic axis, or you can say the optic axis is along the surface or any face. So any question or doubt so far? So and as I said, if we incident a plane polarized light perpendicular to optic axis, a normal incident, then the double refracting crystal will be called as wave plate. Okay, so instead of saying that normal incident perpendicular to optic axis, we'll call optic wave plate. It means the plane polarized light should be incident normally and perpendicular to the optic axis. You have to design, we have to prepare wave plate by cutting or making in a such way that so that we have wave plate. So and then here if you have a wave plate, and then we might be interested to know when they leave the surface of the double refracting crystals, the E and O ray, again they will emerge out the UI component and EX component, as we explained or as we discussed in above. So how much path or phase difference will be created between E and O array? Then you will tell that the path difference between E and O array, and therefore the phase difference between E and O array, will be created depending on the thickness of these double refracting crystals. Okay, so depending on the thickness of the double refracting crystal. So you prepare a wave plate in such a way that the path difference, okay, or the path difference between the E and O array will be lambda over 4, where lambda is the wavelength of the incident plane polarized light. If the lambda is the wavelength associated with the incident plane polarized light, and if the path difference will be created, which is lambda over 4, path difference lambda over 4 will be created between E and O array when they travel inside a wave plate. That wave plate is called as quattro wave plate, because the lambda over 4 path difference between E and O array. And if the path difference is lambda over 2, then it will be called half wave plate. So it means you again make a thickness of a wave plate in a such a way that the E and O array path difference will be lambda over 4. Then we will call it a quattro wave plate. So quattro wave plate is nothing but it's a wave plate which will create a lambda over 4 path difference between E and O array when we incident of plane polarized light. Okay. So and as you, so let's consider for negative type double refracting crystals, which is calcite. That means we will make wave plate by using calcite. So that case, what will be the optical path difference? Delta x will be mu naught t minus mu e t, because mu is less than mu naught. For negative type or positive type, the relation will be reversed. And what is t? T is the thickness of the double refracting crystals. And similarly, for positive, as I said, the relation will be reversed. And so in order to prepare a quattro wave plate using a positive type double refracting crystal, for example quartz, the thickness of this double refracting crystal should satisfy this relation, t equal to lambda over 4 mu minus mu. If we make by using a negative type double refracting crystal, let's say calcite, so the relation will be reversed. So it means we will cut a wave plate in such a way that the relation between the T, the thickness of the this wave plate will satisfy this relation, then it will be called as a double refracting quattro wave plate. Similarly, for half wave plate, we have this relation. So in short, what we understood that a quattro wave plate can create a pi by 2 phase difference between O ray and E rays when they travel inside a quattro wave plate, whereas a pi phase difference will be created between O and E ray if we incident a plane polarized light on a half wave plate. Got it? Yes or no?
Yes, sir.
So what about others? Are they listening or?
Yes, sir. Yes, sir.
Yes, sir.
Because unfortunately we
Yes,
did
sir.
not able to record
Yes, sir.
today's lecture. So it is important to listen. Okay. So this is the summary of the book which I have already posted over Google Classroom. Okay. And again I am repeating because to make your attention. So when we incident a plane polarized right on the surface of wave plate. So now I'll call wave plate rather than double refracting crystal. So wave plate, either quarter wave plate, half wave plate. What will happen? So we'll have E ray and O ray. E ray will be oriented along x-axis and O ray will be oriented along y-axis, because optic axis, assuming optic axis along x-axis. And it will travel E and O ray inside double refracting crystals, and when they leave the other side of double refracting crystal, they will emerge out EX component, UI component. Okay, and because inside double refracting crystal we have concept of E and O ray, but outside double refracting crystals we have concept of EX and UI component rather than E and UI. So we have two components when we incident, and when it touches the plane polarized, it touches on one side of the wave plate. It could be a quarter wave, half wave plate. It will be E ray and O ray, and when they leave the other side of the quarter wave plate, half wave plate, then we will have EX and UI component. Again, they will join, give you a resultant wave. Okay. So now, so when we incident plane polarized, right, and if the theta is 45 degree, what does it means? So the electric field oscillation direction associated with incident plane polarized light makes 45 degree angle with respect to the optic axis. Theta is the angle between optic axis and the electric field oscillation direction of the incident plane polarized light. If it is a 45 degree. What would be the EX and UI component relation? Then you can say the EX equal to UI. And when they leave the other, other face of this quarter wave plate, the phase difference between EX and UI component will be pi by 2. This is actually the phase difference between O and E ray. And when the O and E ray will reach the other side of the double refracting crystal, then it will be called as EX and UI component rather than E and O ray, because as I said, there will be no concept of E and O ray outside the wave plate. So since when this E and O ray will create pi by 2 phase difference, so therefore the phase difference between EX and UI component is pi by 2. They are equal, and this is what is the mathematical condition. Which kind of polarized light? Then it is the circularly polarized light. So it means by using a quarter wave plate, one can produce a circularly polarized light by incidenting a plane polarized light, which makes an angle 45 degree with respect to optic axis of the quarter wave plate. Got it?
Yes, sir.
Yes or no?
Yes,
So now
sir.
what we learn that using quarter wave plate, one can produce circularly polarized light, provided we shoot incident plane polarized light. How can we produce plane polarized light? By using a Polaroid or polarizer, one can produce plane polarized light. And using this plane polarized light, by the help of a quarter wave plate, one can produce circularly polarized light. And if this angle is not equal, that means the electric field oscillation direction associated with the incident plane polarized light and optic axis is not 45 degree. EX component not equal to UI. Still, since we are using quarter wave plate, pi by 2 phase difference will be created. And this is the condition of the elliptical polarized light. So it means by using quarter wave plate or any other angle, one can have electrical polarized light. And then you might ask question, what is the uses of half wave plate? So if we incident a plane polarized over, halfway plate, as per the definition, the pi phase difference will be created, and Ex may or may not equal to be Ui, because it does depend on how much angle it makes with respect to optic axis. If theta equal to 45, Ex equal to Ui. If theta is not 45 degree, Ex not equal to Ei. But since this is the, then you can immediately recognize, so this is the condition of plane polarized, right? That means if you incident a plane polarized light on the surface of halfway plate, you will still have plane polarized light. But what you can observe, the polarization, polarity, you can say, that means that the direction will be reversed because the pi phase difference between Ex and Ui component. So what does it mean? So in order to understand more deeper, let's look at this schematic diagram. So you can see, right, this is a halfway plate, and you can see it makes an angle theta with respect to initial polarization plane, or you can see the optic axis here. And since it is a halfway plate, what you can see, so it is reversed pi. Okay, so the Ex and Ui component, okay, because the phase difference will be this. Initially it has the component, so if you assume this is, let's say, Ex, this is Ey, right? And since the pi by 2 phase difference will be created when they leave, so this will be your Ey now. And what will be resultant wave? The resultant will be something like this. So that, okay, so now the oscillation direction will be here. So the polarity will be changed. So that has been shown here. We have halfway plate. So here the initial oscillation direction. So now we have this is, let's say, Ui component, and this is Ex component. Okay, so now the pi by 2 phase difference will be created. So what we'll have? So Ui component will be here still, and Ex component will be here, because this is the pi phase difference. Okay, because one of the component will be reversed. So what is the resultant? The resultant will be here. So by using a halfway plate, we can still have plane polarized, right? But the polarity will be reversed. Initially, it was oscillating here, making angle theta with respect to y-axis. Now it makes an angle minus theta with respect to x-axis or y-axis. And if you have a quadroid plate, so this angle is not 45 degree. So therefore, we can see the elliptical polarized, right? Okay. And this is a 3-dimensional diagram. Do you able to see it? Yes or no?
Yes, sir. Yes, sir.
So you can
Yes, sir.
45
Yes,
degree,
sir.
and you can imagine, right? So this is the one component you can see going inside the plane of paper, these things, right? So now it touches the surface of the double refracting crystals, right? And now you can see it travels, and you can see how initially it makes an angle 45 degree, and when they leave, you can see how the polarity changes. Okay, so the optic axis here. So you can see, right? So how the polarity changes. Okay. So this is all about polarization, and the idea behind this polarization topic is to understand the basic principles behind different kind of polarized light and how one can produce these 3 different type of polarized light. So what we understood that by using a Polaroid, I did not talk much about Polaroid, right? But we talked about polarizer. But there are many, special kind of, devices can be used as a Polaroid. Even if molecules, okay, molecules, even if including biological molecules, a grid of wires, right, which will be, very narrow spacing, right? So can be used as a Polaroid. That means can produce plane polarized light. And there is a one type of special type of device or optical device one can make from this double refracting crystal called nickel prism. I did not talk about this. By using the nickel prism, one can also produce plane polarized. Nickel prism, so one can construct by using a double refracting crystals, right? So that means we have two plane polarized, right? In the process of transmission, you use the concept of the internal reflection to diverted one of the plane polarized light, either E ray and O ray. So one can have only one polarized light, either E and O ray. So one can use nickel prism to produce plane polarized light, right? And by using quadroid plate, one can produce circular and elliptical polarized light. Or if someone wants to change the polarity of the plane polarized light, one should use half-wave plate. Okay, so any question? Hello? Any question? Am I audible?
Yes, sir.
Yes, sir.
Yes, sir, you're audible.
Yes, you are audible.
Yes, sir.
Okay, unfortunately, I did not record today's lecture, but don't worry, I will post the lecture slides and you read it, and you also go through the study material, and whatever I have discussed under this polarization topic, most of the content I have borrowed this uploaded material, which is the portion of the Ajay Ghatak book. Okay, you can also go through it. So in the next class, we will be discussing the second unit, namely quantum physics. So do remember the unit 1. This is actually more than 40 percentage of the entire syllabus. You can say the 45 percentage. So it is almost 45 percentage of the entire syllabus. So it means we have covered the 45%. Other 3 units, the quantum physics will spend 12 lectures, and then electricity and electromagnetism and electromagnetic wave, hardly 6 to 7 lecture, and then statistical physics again 5 to 6 lecture. It means the more than 45% we have covered, and the rest 55 to 60% will cover under unit 3, 4, unit 2, 3, and 4. Okay, so I think we should I should stop here. So we'll meet in the next class. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.